And first up is projections of reality.
There we go. I want to take about 10 minutes to talk you briefly through what we've been doing over the last couple of days. But I wanted to start by thanking everybody on the cluster who did work with us over these, come on this slightly mad journey. And particularly I wanted to thank Nesli and Emilia from UCL who helped us with the whole setup, and Jessica who made sure we actually have material to show you this afternoon on screen. Projection of reality, what is it all about? The reality in our case were these white styrofoam boxes, and both in their physical reality as well as in their sort of hidden analytical reality, where we're trying to understand what happens if we start manipulating these boxes and we have a live feed of analysis projected back onto those elements. There are three major parts to the project that my colleagues will talk to you about in a second. First is the collection of the geometry, the scanning. And I think the trick was to try and get to a geometry which is as simple as this. So a cube is being described by 8 corners only. There's an analytical component naturally where we developed a number of types of analysis within the cluster. In reality, the way the workflow was set up, we very consciously make the decision to try and keep the scanning and the analysis separate. So the analysis that you're seeing today are examples, but the workflow lets you plug in any kind of analysis that works in real time. And lastly is trying to get that analysis back onto those boxes fast enough and as precise as possible within sort of a real-time environment. I'm going to pass over to Richard, who will talk to you about how we collected the geometry in the first place.
So perhaps one of the key phases was scanning these objects, and because everything else flowed from that. And on Monday morning, we had a process in place that used Firefly, a plugin for Grasshopper, and that could scan, that had a resolution of 60 by 80, so about 500 points. And the latency of moving one of these boxes was about 2 to 3 seconds. So when you'd move it, take a few seconds, and then it would update on the computer. That wasn't quite interactive enough, and so we needed to come up with something that was fast and accurate. So we used a Connect sensor, and you get about 400,000 points from a Connect, 640 by 480. So we cropped that down to 100,000, and if you'll indulge me for just a moment, because normally I only get to talk to my wife about these things and she just glazes over. Hopefully you guys might be more appreciative, I don't know. 100,000 points per frame, keeping memory of as many frames as we want without slowing down the computational time, was 125 million numbers per second, and we're able to discover and cluster these objects and be able to reduce 125 million numbers down to 8 per object. So if you had 10 objects, 80 numbers. This is real time, it's linear, not exponential, so you can scale it up. We might have reinvented the wheel, who knows, but we had fun doing it, so that was good. Once we had that minimum data needed to define the boxes, we needed to actually clean it. The feed that came in from the Connect was a bit, well, it was dirty data, and I don't like dirty data, so we had to try and wash that and clean that, and we had to have a memory of where the boxes slightly were, so when you moved it, it would realise that it had moved, but when you weren't moving it, and the sensor thought it was moving, it would know that it was staying still. And all of this, again, is in real time. And once we had these objects defined by just a few points, we were able to pass it on to the analysis part. So some screenshots. There are some of the boxes on the table. We also had some hand tracking, which we built in to control some sun paths, which we'll show a bit later on. And you can see on the on this one, you can just see the outline of the boxes just starting to be discovered by the algorithm. This was before we really cleaned up the geometry. Some more screenshots. We might have a video. There we go. So here's a sensor tracking the hand. Here's some object detection. We weren't drinking 10 cans of Red Bull a day. These videos have been sped up. And if we just watch that one again, you can see on that final one that when you combine these boxes, the algorithm detects that and recognises that what were 2 boxes are now 1 box, which is useful to break things apart, join things together. You look down the bottom about now. And passing over to the analysis. Dominik.
As we wanted to create an environment that enables people to get together and to see the immediate reaction of the urban environment or whatever environment to their design decisions, it was quite crucial for us to get an interface which was fast enough to operate between all those different members of our whole project. So basically we use this OSC protocol, which is very widely spread, and it's quite very easy to take all these points that we get from the scanning and feed them into other programs. Like in our case it was Blender, Grasshopper and Rhino, and processing via Eclipse. And so we had different types of analysis running. So we had the visual analysis in Blender. We had also visual analysis in Grasshopper and Rhino, ISO-VIST mappings, density maps, and pedestrian flow, sun position, and sun radiation in processing. And as we have processed all of this stuff, we need to feed it back into the whole environment. So this was done by UDP protocol, which is also very easy. We just passed point informations, and RGB color values just by strings that were updated like 25 times a second. So so here we have a video showing some of the analysis that we did. The solar incidents. So you could see the solar impact on the data. So we had ISO-VISTs basically having viewpoints and showing the amount of visibility you have. This is also visibility analysis combined with the distance map. So I replay it again. It was, I think, a little bit fast. Here we go. No. Here. So solar, basically we had the possibility to change the sun position and have the immediate feedback on the solar radiation. These are the ISO-VISTs. You have different viewpoints. And again, visibility analysis. So we also had an agent model, which was quite nice to see, because we had a start destination and we had an end destination, and we had like hundreds or 200 agents running across the screen. And as you move those boxes, you could obstruct the pedestrian flow, and that was quite a nice thing to see. This is again the visibility analysis with the viewport in the middle. So if you move the viewport, you basically get the different buildings colored in different colors according to the position of the viewer. This was our Grasshopper definition that we wrote to read the stream coming from the object tracking. So this is also a video. Can I have a look at it? So we used a G-hole for getting the stream. And then basically we used separators to separate the different points of the object. So we just had to split the string, and that's quite a super easy task to do. We had some more analysis, again on the top, the sun radiation, then we had the ISO-VIST, and on the bottom the distance and visibility analysis again. Yeah, and we fed this all back in or via the UDP protocol to take over to the next and last part, which is the rendering system. And I hand over to Lukas now, which will tell you more.
So here in the rendering section, we get the data from the analysis, and we get it as x, y, z coordinates, and per coordinate we also have a color value, so that gives us a colored mesh in the end, and we would render that in that part with OpenGL in a framework that was written for that workshop. And well, here we have a video, so I would quickly just show you how the setup looked like. Oh, first the calibration, sorry. So here you see how the calibration is done. It's a bit fast, but what you mainly do is you have a virtual model and the real model, and what you need to do is to make them match. So you have the yellow points that you can see here that are telling the system how the virtual scene must be transformed to match the exact physical scene. So you do that 6 times, and when you have 6 points, then the virtual scene map to the real scene. So that's what you can see here. And then we had some projection tests running. Here you can control the sunlight position with your hand, and we also had some volume tests just to make sure that our concept was really working. And here you can also see the visibility analysis. Here what you can see is the UTP protocol running on the bottom to get the data into the program. And then we also have a small video of the exhibition yesterday where people were trying this in real time. So here you can see whenever somebody's moving the styrofoam box, of course the color will update, and if somebody moves the hand, the shading will update. Yeah, that's it. Thank you.